Hi, welcome to my latest video, all about volumes of solids and how we can obtain them. Have you ever thought about how we obtain a particular formula for the volume of a three-dimensional shape? For example, here's a cylinder, radius r, height h. What's the formula for the volume of a cylinder? You may have used it already. Volume is pi r squared h. Do you know of another common three-dimensional shape? Cone? To work out its volume, we need two values, the base radius r and the height, h. What's the formula for the volume of a cone? There it is. Volume is a third pi r squared h. And finally, another common shape, a sphere. All we need to know for that one is the radius. Do you know the formula for the volume of a sphere? 4 on 3 pi r cubed. Three very well-known formulae. But where do they come from? We're going to obtain each formula by using a very well-known method. Here is rotation about the x-axis to produce a cylinder. Rotation about the x-axis again to produce a cone shape using a straight line. And finally, rotation about the x-axis to produce a sphere. Now the first stage is to consider rotating a two-dimensional shape either in the x-axis or in the y-axis. Let's suppose we rotate it in the x-axis first. There's a shape. Rotating it about the x-axis means it will look like that. We produce a three-dimensional object. Now let's see if we can rotate it in the y-axis. Same shape, same two-dimensional shape, and that's what it will look like. So the first consideration you must have is whether or not you will rotate a two-dimensional shape in the x-axis or in the y-axis. Sometimes it doesn't matter, sometimes you don't have a choice. It has to be either one or the other. Now let's obtain the actual formula that will give us the volume of a three-dimensional solid. And we'll consider the case first by rotation in the x-axis. There's the object at the top in black, and at the bottom it's been rotated. Now remember, we've created a three-dimensional object, and if we look at a slice of that three-dimensional object, it will look something like that. A slice will have the shape of a circle, and let's call the radius of that circle y, the y value of our function, y equals f of x. What we're going to do is to work out the volume of that solid between the x values a and b. Firstly, the area of the circle is pi y squared, because we know the area of a circle is pi r squared and the radius in our case here is y. So the area of the circle is pi y squared. Of course, what we want to do, what we want to happen, is to obtain the sum of the infinite circles of different radii. And that's what that symbol means. Integrate. Have you come across that? We integrate to obtain the sum, the exact sum. So what we're going to do is integrate our function between a and b to obtain the volume. And of course the volume means obtaining the sum of the areas from a to b. Now how is that formula useful? Well, we'll look at that in a moment. Now let's look at a similar case where we rotate in the y-axis, and we can do a similar sort of thing. There's a slice parallel to the x-axis, a circle again, but this time the radius is x. There's our function y equals f of x, and we are going to sum the areas of the circles between a and b along the y-axis. Again, the area of the circle is pi x squared this time, because the radius is x, and the volume we want is the integral from a to b of pi x squared dy. That means we are integrating with respect to y. We are going along the y-axis. Okay, so we've got two formulae, haven't we? One for rotation about the x-axis and one for rotation about the y-axis. So it comes down to choosing the appropriate one depending on what the problem is that you have to solve. So let's do some. First of all, the volume for a cylinder. Can you see what two-dimensional shape we might use to rotate to create a cylinder shape? Here's one that will work. We have a horizontal line with equation y equals r. R is a constant, and if we rotate that about the x-axis, we will obtain a cylinder shape. And what we will do, of course, is to integrate it from x equals 0 to x equals h. There's the formula for rotation about the x-axis. Now, one problem is that to integrate, we must have the same variables being used. That means either x or y. We can't have both. So what we're going to do is to substitute an expression for y squared. Well, we know that the equation of our horizontal line is y equals r, so y squared will be r squared. So we can substitute that for y squared, like that. And of course, our values for a and b are going to be 0 and h. Now to integrate that, keep in mind that pi and r are constants, so really, to integrate that expression, it's going to be pi r squared x between the values 0 and h. So we will substitute h for x and then substitute 0 for x. And remember, there's always a minus in between, and that gives us the formula we expected, pi r squared h. So the volume of a cylinder of radius r and height h is pi r squared h. Alright, one down, two to go. Now let's work out the formula for the volume of a cone. And to do that, we can take a line and rotate it about the y-axis. The equation of the line that we will use is y equals h over r x, where h over r is the gradient of the line, r is the radius of the cone base, and h is its height. So rotating about the y-axis means that's the formula we will use, pi x squared dy, the integral of that, between a and b. Our values for a and b will be 0 and h, but we need to substitute for x squared. Well, we know the equation of our straight line is y equals h over r x, so x squared will be what's shown there, r squared over h squared, y squared. So substituting all this information into our expression for the volume, that's what we obtain. And integrating that, remember pi, r and h are constants, so all we're doing is integrating or anti-differentiating y squared, which gives us a third y cubed, doesn't it? You add 1 to the power and divide by the new power, and that's what it would look like. And now we substitute h for y and 0 for y and subtract like that, and simplifying that, h squared in the denominator will cancel with h cubed at the top to leave h, and we're left with a third pi r squared h, our formula for the volume of a cone. Okay, that leaves us with our third one, the volume of a sphere. What do you think? Rotation in the x-axis or rotation in the y-axis? In fact, in this case it doesn't matter, because of course a sphere, or its two-dimensional equivalent, a circle, is symmetrical everywhere, isn't it? But I've chosen to rotate the semicircle in the x-axis. That means the semicircle radius r rotate in the x-axis. And the equation for our circle is x squared plus y squared equals r squared. That's a circle of radius r with centre at the origin, 0, 0. Alright, so rotation about the x-axis, that's the formula we will apply. Again, what do we substitute for y squared? Well, we can rearrange our equation for the circle. X squared plus y squared equals r squared. Rearrange gives us y squared equals r squared minus x squared. And of course, our values for a and b will be negative r to r. making those substitutions, that's what it will look like, and integrating, and now substituting r and negative r. Be careful with the negative signs here. That's what it will look like. And then it's just a matter of carefully simplifying all of that. That's the first stage. And you can check this out, but when you simplify that last line, you will obtain 4/3 pi r cubed, which of course is our well-known equation for the volume of a sphere. And just to finish, here's one that we haven't looked at. On the left, in the first diagram, we have a paraboloid. That's basically a parabola rotated in the y-axis. What we're going to do is to show that the volume of the shaded part of the paraboloid is equivalent to the difference in the area between the two squares shown at the bottom left. Where would we start? Firstly, because we are rotating in the y-axis, the formula requires the two y values for our limits of integration. Now we know the two x values, the square root of a and the square root of b, so to find the equivalent y values, we substitute each of those x values into our equation y equals x squared. So if we substitute the square root of a for x squared, y becomes the square root of a squared, which is a. Similarly, if we substitute square root of b for x squared, we obtain y equals b. So there are our two limits of integration. Now here's the formula we will use for rotation in the x-axis to find the volume. Again, we substitute for x squared. We know that y equals x squared, so that's an easy one. And also our values for a and b will remain as a and b. So that's what we have. Now integrating, if we integrate y, we get a half y squared, and then substituting b and a and taking out a factor of pi on 3. Okay, so there's our volume for the shaded part of the paraboloid. Now let's see how that ties in with our area of the squares. The area of a square, of course, is length times width, same as a rectangle. So the area of the largest square is b squared. The area of the smallest square is a squared. And the difference between them will be b squared minus a squared. And let's call that AB. So it's easy now to see that VP, the volume of our paraboloid, is pi on 3 times our AB, the area of the difference between the two squares. I hope this provided some insight into how effective this method of finding volumes can be. Until next time, bye-bye.